Hello everyone. So far we have learned how to increase the volume for products of the gasoline and how to improve the quality of the product by many kinds of reactions. So in this chapter 9, we will come to the part of blending products. Before going to the material of this chapter, I would like to ask students to in two questions. One, you have to list all kinds of fuel oil sold in the gas stations, and also what kind of specific properties that used to classify those type of fuels. Actually, I have listed that here. According to the website of Apple and also the website from Bangja Petroleum, we can see that actually there are several kinds of gasohol and also the benzene octane 95 sold in the gas station as well as the diesel oil. According to the gasohol sold in the gas station, they are classified into 91, 95 in different oxygenate amount. So you would have the idea that specific properties that used to classify the different types of the gasohol based on octane number here. Okay, let's get back to the properties. According to the textbook, about 9 to 10 properties are listed for the blending concern, and what we will study here, only 5 of them will be due in more detail. Let me go through the definition of them a little bit here, starting with the RVP, or what we call is reed vapor pressure. The reed vapor pressure is defined for the gasoline evaporation characteristics, and the EPA, Environmental Protection Agency, regulates the vapor pressure of the gasoline sold at any retail store, gas station during the summer season to be low. This is just to prevent the evaporative emissions of the gasoline that may contribute to the ground level ozone. In case of the state of Texas, where may be applied to Thailand climate, the RVP is set around 7 psi and not higher than 7.8 psi. However, in wintertime, RVP in some states is required to set high. This is just to increase the volatility of the gasoline to help the ignition properties for that kind of fuel during the combustion. And of course, we mentioned before that RVP is the vapor pressure measured at 100 degrees Fahrenheit. Now let's go to the octane number. There are two kinds of octane numbers, starting with the model octane number, which is measured at more serious operating condition. And of course, this is the number obtained from the test is run at 900 rpm engine speed. So this number is more representative of the performance of gasoline when used in automotive vehicles operating under load, while the ROM research octane number obtained from lower RVP of 600 RVP of engine speed. So well, we can see that the ROM will have the value higher than the I'm sorry, the MON will have the value higher than ROM, 8 to 10 points. For the octane number that we use for the specific properties, as I mentioned in the previous slide, this number shown in any gas station in the gasoline dispensing is the average of the gasoline ROM and MON. How about the flash point? The flash point is the lowest temperature at which it can vaporize to form an ignible mixture in air. So this number is generally used for how to keep the gasoline safely. And in general, the flash point is around minus 40 degrees Fahrenheit or minus 40 degrees Celsius. Gasoline is, of course, flammable liquid. Even at the temperature as low as minus 40 degrees Celsius, it also gives off enough vapor to form a combustible mixture in air. How about pour point? This temperature is the lowest temperature at which and petroleum product will begin to flow. So what do we mean is how much the paraffin is contained in the fuel, or the paraffin can be crystallized to this point when the fuel gels becomes resistant to the flow. So the pour point also varied about 10 degrees Fahrenheit to 20 degrees Fahrenheit below the cloud point. We will not mention about that. Actually, these two properties is generally show up in diesel fuel rather than in gasoline. Of course, the viscosity, this is the one that will be concerned in both gasoline and diesel. Okay. Well, I don't have our gasoline and diesel properly sold in the retail gas station here. So what I am showing here in this slide is the data by the AFDC Alternative Fuel Data Center from the Department of Energy in the US. You can see that larger range of the carbon composition is found in diesel oil, diesel fuel, and higher boiling point as well compared to the gasoline. The RVP or vapor pressure is liquid properties of gasoline, of course, but not much in diesel. This number is regulated upon different climates, as we talk about that. Gasoline sold in US is mixed for the octane number from 96 to 86 to 94, while our country is set only 91 and 95. And then the flash point, which is about, of course, minus 45 degree Fahrenheit. And other properties are about the energy obtained from its combustion. So I just leave it. Okay, we back to visit this refining process again, and you will see that some C4 isomerate, reformate, alkylates, and FCC gasoline and coke gasoline will be mixed in the gasoline pool here. Portion of each product here will be calculated to make sure that the final products will meet the standard of quality. What I mean is, of course, octane number, flash point, RVP, so on, and viscosity. Let's go to this table 9.1 in the textbook, and this table lists what type of products that could contribute for the final products and what their RVP and the octane number are. For example, you can see that LSR gasoline will have a little bit high in terms of RVP but low in terms of octane number. But when we look at the alkylate, we do have low RVP but high in octane number. So the combination of this will be what we get in the gasoline pool. Well, when they are added in the gasoline pool, the way to calculate the mixing properties cannot do by the adding technique. You have to use the index of blending first. So the diagram show the way of calculation will be in the next slide. You have to start with converting the properties into a blending index, and then you can make a summation of that because we have several part of product come together and mix in the gasoline pool, so we have to make a summation of it, and then finally we have to convert back to its properties. Okay, you may confuse on this diagram, but let's see in the example. This example, we have gasoline from different sources, and we would like to know what would be the final RVP after mix them together. So from the list of light state run gasoline, heavy state run gasoline, and reformate, and also FCC gasoline, they mix together at this portion, and by that kind of products we know what the RVP for each one are, and then we need to convert that to the blending index. So the way to do that is to find out the blending index of RVP equal to its RVP to the power of 1.25. For example, this way. We have 11.1 to the power of 1.25. So what we will get is 20.26. Do that for the rest of the products here. So after that, we do the summation by using that blending index blend. Of course, now we can use the summation based on the volume fraction. So what we have is the volume fraction here multiply with that. So what we get is a fraction of blending index. And then after that, we will sum of this. And then what we have here is blending index on this side. And then we reverse to the RVP in the final. So what we have here is, after mixing that together, the final blending RVP is about 8.4. Now let's go to other properties like flash point, pour point, viscosity. We also require to use the blending index as well for each one. To convert first before do the summation based on in this kind of flash point we use mass fraction, we use volume fraction and volume fraction for pour point and viscosity. How about octane number? Come to the main properties of octane number. I also put the table of oxygenates, which are important here. So as you can see, there are two kinds of oxygenate. One is alcohol and one is ether forms. Okay, they both have very good in octane number. Most of them higher than 100. So sometimes add a little bit of this will it can be adjust the octane number of the product easier. Now let's say there are two types. Okay, to convert the octane number to the blending index octane number. In this method, it's quite direct use. So it depends on what kind of octane number of that products that you would like to use. Yes, for example, if we are looking for light state run gasoline, which have the octane number around 61 to 67. Okay, remind you again, we are using light state run gasoline. The light state run gasoline has the octane number about 61.6. So in this case, we have to use this equation 9.20a to calculate for the blending index, because the octane number is fallen in this range. After that, we do the summation based on the volume fraction. In the other type of method, this method is using the components. And now we don't have the blending index, but just use the linear summation right after. So what the difference here is the information like how much the olefin aromatics present in the mix in this kind of products are required. So after we know that O and A here, we can, and also the octane number for each one. So we can put that in this equation. And then we can use the summation of this in terms of volume fraction. Okay, this example showing that we would like to mix the alkylate, coker gasoline and FCC gasoline together in this portion. And of course, the after checking what the RVP for each one is, it is about 97.3 for the alkylate, 67 for the coker gasoline, and 83 for the FCC gasoline. So what we do first is to select what equation that we're gonna use. So in terms of alkylate, we need to use 9.20b to calculate for the blending index. In terms of coker gasoline, this equation will be used. How about FCC gasoline? This equation will be used again. So what we get after that, we will get the blending index for octane number. And then we have to find out for the volume fraction of this. And then multiply them together. And then summation of that. And then after that, we do convert back. Alright, in this example, we are looking for the properties after the blending. How about in this example? In this example, we would like to know if we have like state run gasoline and hydrocracker gasoline in 3,000 and 2,000 barrels, and we want to know how much of FCC gasoline and N-butane should be put in this to make the final product that have RVP equal to 12 and viscosity equal to 0.525 centistroke. Okay, so what we do will be the same. Okay, actually this example can work on two equations, two unknowns, and solve simultaneously. However, we can do the other way by using linear programming to solve the problem. By using objective and constraint equations, right? So let's redo to in this Excel. Okay, what we have to do first is convert the RVP to blending index, and this is quite simple because it's just make that to the power of 1.25 and then copy that. How about the blending index for viscosity? For the blending index for viscosity, will be based on log of the viscosity divided by 3 plus log of viscosity. Okay. Alright. And each property, same thing here. And log of 3 plus okay. I put the yellow one as the given information. Next step is to assume that this is about 100 and this is about 100. We assume that first. So let's make it in in this color. And then we have to make the objective equation. So in objective equation, it means this input multiplied with that should be this input multiplied with this. That should be the first objective, with the constraint of this volume multiplied with the blending index of viscosity, and should be equal to this number multiplied with the final viscosity here. So let's see. Equation should be that multiplied with this plus this multiplied with this plus this multiplied with this plus this multiplied with this. Okay. Should be equal to this multiplied with the blending index of the final one. Okay. So let's make it minus of this plus that plus this multiplied with the blending index. Okay. The same thing to the constraint equation, which will make to the viscosity. Okay. Multiply with this. Alright. Then minus of this plus and multiply with the final viscosity. Okay. Then we go to the data. Okay, now we can go to solver, but you have to add it in first. So go to data and then go to solver, and then the objective is this, and we will set that equal to 0 by changing these two values, and then add the constraint here, which is that will be equal to 0 as well. Okay, that's it. Now what we use is linear programming and go. Based on that, we will, let's do it again. Actually, we already have the number show up here, but let's do it again. Okay, so now you keep the answer. So the answer is we do need to add FCC of 6,000 and also N-butane of 640 barrel. And if we add that, the RVP final will be about 12 and viscosity final will be about 0.5 to 5 centistroke. Okay. Let's see. In case that in case that I just want that to be one parameters. So let's see what should I get. So I assume that to be 100 and to be 100. Now we cannot use the two equations, two unknowns to solve this problem because we have x, y, z as the unknowns. We have three unknowns right now, but only two equations. So can we do the same thing here? Yes. But the value changing cell starts from 44 to 46. And then we do the evaluation. Oh, let's see. So in this case, we don't need any hydrocracker gasoline to add into that. But we require to have only FCC and N-butane. But the product that we have here will be not big. However, we can put the constraint on this by adding that. So this one should be higher than 1/800. Let's see if we can get. Okay, this is another constraint. Go. Alright. See that in case that we do have hydrocracking gasoline, we also can increase the probability of what I mean is the amount of the products. I think this is quite useful, so you can play around with the solver. Okay. Alright, that's all you have to try using this linear programming on example 9-13 and 9.14 to make sure that you understand. Alright, thank you and goodbye.